So I'm going to be talking about a deflationary account of quantum theory and its implications for how we think about the role played by the complex numbers. This is based on a series of papers. This image of Magritte's pipes, "Ce n'est pas une pipe," has become kind of a mascot for this project, to the extent that we have a student who actually crocheted me this image, and it's sitting in my office. I'm going to get started because there's a lot we're going to talk about. So actually, I'm going to do something totally unrelated to the talk. This is fresh information from incoming students to Harvard's physics PhD program. We actually made this a mandatory question as part of their registration, so every student filled it out. So this is an exhaustive survey. But we're just curious, like, what do you think about the measurement problem? Is the measurement problem a major ongoing problem, a minor ongoing problem, a solved problem? You can see some of the responses here. You can see that almost half regarded as either a major or minor ongoing problem, which I think is progress, right? These are physicists, not philosophers. Remarkably, only one student said it was a solved problem, and I should say that I talked to the student afterward, and he misunderstood the question, and he actually changed his mind and said it's an unsolved problem. So actually, we're good. I know this is supposed to be. Yeah, we're good. We're making progress. Excellent. Yes. So there's a bunch of other responses here. This is unrelated to quantum mechanics, but I was curious what they thought about the flow of time. I thought it was interesting that about half of them agreed with Einstein. That may be because I mentioned Einstein's name and who wants to disagree with Einstein. And I asked about preferred interpretations of quantum theory. I think it's telling that about half of them picked either the orthodox or Copenhagen interpretations, which for most of the incoming students probably they regarded as essentially synonymous. Among the non-orthodox or Copenhagen interpretations, the plurality was the many worlds interpretation, which is that orange wedge, and everything else is basically a thin sliver. Anyway, so I can give you this information later if you'd like. All right, now to the main course. All right, so this is the outline of my talk. I have a lot I'm going to talk about, so I'm going to move expeditiously. Okay, so let me start with the complex numbers. So this is just going to be a quick review, but it's useful to just get everything clearly on the table. So roughly speaking, an algebra, as we know, is a vector space with rules for addition, multiplication by scalars. What makes it an algebra is that there's also a multiplication rule that takes two elements of this algebra, two vectors, and returns another vector. A normed division algebra has a norm operation that maps the elements to non-negative real numbers and includes for every non-zero element a multiplicative reciprocal so that we can do division. Right, that's what makes it a division algebra. A key example is the set of real numbers R, which form famously a 1D division algebra with norm given in the following way. Right, that's the real line. We're nice and happy with that. There's a unique 2D normed division algebra. It's constructed along with the other normed division algebras of the Cayley-Dickson construction, and its uniqueness is guaranteed by the Hurwitz theorem. This is called the complex numbers. Addition is defined entry-wise, so they're 2D, so these are ordered pairs. We have entry-wise addition. We have multiplication by scalars, which is also entry-wise, and of course we have multiplication together, which is also entry-wise. Oh, no. Actually, wait a second. That's a problem. No, if we do that, then there are no reciprocals for non-zero elements of the form a comma 0 and 0 comma b, so that doesn't work. Instead, we need to take our multiplication rule to be as follows, and from this point of view, it's a little non-obvious this is the correct multiplication rule, but indeed it is the correct rule. I'm using color coding here to help your eyes track what's going on a little more easily. We introduce a complex conjugation operation that flips the sign of the second component. We introduce a norm given in the following way. In so doing, we end up with a commutative norm division algebra with a commutative multiplication rule, but we do give up something. We give up the ordering that you have with the real numbers. You can't order these numbers, these so-called complex numbers. The real part refers to the first component, imaginary part to the second component. This is all review. I wanted to all get this on one slide, though, because this is what I take the complex numbers to be as an algebraic structure. Notice I haven't said anything about, well, in a moment, I or anything like that. Now, of course, we can represent the complex numbers in a variety of ways. Any set of mathematical symbols that are in a one-to-one correspondence with these ordered pairs and exhibit the same properties give a representation of the complex numbers. To construct the most familiar representation, we'll just denote 1 comma 0 to be 1 and 0 comma 1 to be I. When we do this, we can take combinations, our ordered pairs x comma y, and write them. We can repackage them together into a single number-like entity called z, which is x plus iy. One then has I squared equals minus 1, so one can formally write the mystical-looking formula I equals the square root of minus 1, but there's something mysterious going on here. Under the hood, we just have ordered pairs with the special multiplication rule. Good. So this is, again, just review from the Taylor series. We obtained the Euler formula. You've probably all seen this a million times. I just want this for completeness. This leads to the famous Euler identity, which we all know and love. We have the polar form for complex numbers from trigonometry. right? We just draw a little right triangle with an angle theta. We can express all of the x, y. We can express the two components x and y in terms of the length of the hypotenuse of this right triangle and the opening angle. Then we can write our complex numbers in polar form, and this just gives an opportunity for me to mention that we have a radial part of our complex number, which is its norm, and then an e to the I theta part, which captures the angle. It's called the phase part. We'll need that later. Phases have unit norm, and taking the norm of a complex number erases phase information. This will also be important for later. Okay, so this is all just hopefully review. Now, this may be not review for everybody. Maybe not everyone knows this, but there is another representation of the complex numbers. Here I introduce these 2x2 matrices. So one is the usual 2x2 identity matrix, and then I is this weird other matrix that's off diagonal. You can then write any complex number in this way as a 2x2 matrix. And remarkably, these 2x2 matrices, when you use the usual rules of matrix addition, multiplication by scalars, and multiplication, have exactly the same arithmetic properties as the complex numbers. Complex conjugation is carried out by the transpose operation. It comes prepackaged with the transpose operation. We can extract real parts and then therefore imaginary parts. Determinants give you norm squareds. It's a very beautiful representation. And by the way, you know the 2x2 rotation matrix, that's actually just a representation of E to the I theta. That's the Euler identity. The rotation matrix is literally capturing this fact. Okay, so the 2x2 matrix here is called a linear complex structure. Gilles actually mentioned this already. Notice it doesn't involve any literal appearances of I. It only has real numbers in it. But the complex numbers as an algebraic structure, I've emphasized what makes them the complex numbers is that we have a set of symbols with these algebraic properties. It's all still here. We haven't gotten rid of the complex numbers. This is always available. It's always something we can do. It turned out to be useful to introduce an operator K that implements complex conjugation. Craig, this is for you. So we introduce an operator K. As it moves past a complex number, it complex conjugates it by construction. K anti-commutes with the imaginary unit I. Ki equals negative Ik. It follows that the three symbols Ik and Ik generate a Clifford algebra known as the pseudo-quaternions. And I'm citing a paper that Jill actually also cited before, Stuckelberg from 1960. He noted this. So this looks just like the quaternions, but with a little bit of a twist. There's some extra signs in here. By the way, in our real 2x2 matrix representation, K is also represented by a real matrix. In fact, it's just the sigma x, the x Pauli matrix. So introducing K doesn't actually introduce any quote-unquote complex numbers into our real 2x2 representation. Now let me say a couple of things about this Renew et al. Paper, and I'm going to be even harsher than Jill about this. So in 2021, Renew et al. Published a paper in Nature titled Quantum Theory Based on Real Numbers Can Be Experimentally Falsified. The paper had 8 authors. It is one of the most poorly written papers I've ever written, that I've ever seen. So it's incredibly poorly written. It makes it hard to see it's actually based on a completely trivial argument, and I'm just rehashing what Jill has said. You consider several quantum systems. For each, you replace I with a linear complex structure. You claim this gets rid of the complex numbers, but as I've explained, it doesn't get rid of the complex numbers. They're still there. They're just represented now with these matrices. As noted by many people, Stuckelberg, but also more recently in a beautiful review by Mehrheim in 1999, this gauge choice, when you make it, you have to give up certain other ways you do quantum mechanics. You have to give up being able to use factorizable pure states for uncorrelated systems to get empirically equivalent results. What they do in the paper is they erroneously demand that you don't need this. They obviously break quantum theory by making this change and then demanding you still have factorizable pure states. Obviously, you're going to be able to get wrong predictions, which they show. You claim to have falsified real quantum mechanics, lots of hype, lots of attention, and then you get published in Nature. This is apparently how things work, which is just great. Okay, that's all I want to say about that paper. So let me move on and talk about Markovian embeddings. This is the real main course of the talk. So let me start with a second-order discrete deterministic system. So consider a discrete system with configurations X. I'll use color coding here. X is the configurations. Going from 1 through n, just take n to be finite for simplicity, making up some configuration space C. It's a set of configurations. I'm not a configuration space realist. C is just a set that collects all the possibilities. For my dynamics, suppose the system has second-order deterministic dynamics. So the configuration at time t plus 1 is some function involving the configuration at time t and the configuration at the previous time t minus 1. So this is second-order deterministic dynamics. We can always make the following nomology. Nomology is laws, ontology, what exists. We can always make the following nomology, ontology trade-off. We can simplify our dynamical law, make it first order, or first order means Markovian, that's what that means. But the cost is to complicate our configuration space and also make our ontology a little murkier. So in our new kinematics, we'll introduce states now, which are labeled by x and a new variable y, making up a state space that lives in the Cartesian product of the original configuration space and a copy of itself. The new dynamics is going to be that that x at t plus 1 is equal to our function where we plug in x and y. And our new variable y at t plus 1 is just x of t. You can see that this is going to be equivalent to our earlier equation, but it's two equations that are first order in time. We call this a Markovian embedding. And I want to point out that it leads to a new emergent set of transformations. We can now define invertible changes of variables that mix up x and y, right? And this is going to make the ontology very difficult to understand. Okay, so I'm going to immediately generalize this, and I'll have some more remarks about this. But now let's go to the continuous case. So same exact deal, except that we have a continuous system. We'll assume second-order dynamics for a continuous system. That means we're talking about a second-order differential equation. This is very similar. X double dot, that's two time derivatives as some function of x and x dot. Again, we can make a nomology-ontology trade-off. We introduce states labeled by x and y on a Cartesian product state space. Our new dynamics is going to be a pair of equations. Each of these is now first order in time. You can just see this is a trivial rewriting of our previous equations. Again, we call this a Markovian embedding. And again, it will lead to new emergent transformations we can define that will mix up x and y. This is, after all, just what we do in writing a Newtonian system in the Hamiltonian formulation. This is the gist of what we're doing there. All right. So again, this is a nod to Craig. So we can define time reversal transformations. You fix any time t naught, and then you consider time translations. We can translate to the future. We can imagine translating to the past. This is borrowing the way that, in very brief, that Brian Roberts talks about time reversal transformations in his book, Reversing Time's Arrow. For simplicity, I'm just going to take t naught to be equal to 0. So just setting t to minus t. Then a time reversal transformation means that we consider a new solution that is our old solution, but with t and minus t switched. X stays the same, except that its argument flips. X dot gets an x or minus sign from the time derivative. X double dot gets two minus signs, which cancel. The original second-order dynamical law transforms in the following way. We get this modified version of the dynamical law. And so we see right away that the system's dynamical law is going to be time reversal invariant if that function, regarded as a function of these two variables, has this property that it's insensitive to the sign of the second variable. Okay, but now let's rephrase this time reversal for the Markovian embedding. So we have this equivalent Markovian embedding. We replace x and x dot with x and y. This is how these variables transform. The first order, now Markovian dynamical laws transform in the following way. And this is going to be equivalent to what we did before. In fact, we can see that we have time reversal invariance exactly if our function treats y and minus y the same. Okay, so this is just a rewriting of what we did before. And now we're going to see the emergence of the complex numbers. So notice we can combine x and y using the imaginary unit. We can combine y of t with our original dynamical function f as a new complex value thing. I'm regarding it as a function of z and z star, which is equivalent to regarding something as a function of x and y, because if you know x and y, you know z and z star, and vice versa. One ends up with a single first-order Markovian law. We can now take both of our previous equations and write them as just a single complex valued equation, which is very nice and beautiful. So I'm going to simplify the dynamical law quite a bit at the cost of making the ontology murky, introducing the complex numbers in the story, and also introducing this emergent set of transformations that can mix x and y. And so someone just hands you this sort of a system, you might be confused about what it's supposed to mean ontologically. By the way, this complex form of the dynamics is particularly nice when you want to think in terms of time reversal transformations. So these are our time reversal transformations. These time reversal transformations entail that z transforms with y changing sign, the imaginary part changing sign, and x staying the same, which corresponds to acting with a complex conjugation operator. And so we see that a time reversal transformation involves both changing t to minus t and also acting with a complex conjugation operation. The first order dynamical law transforms in this way, and once again, we had a statement about what it means for the dynamics to be time reversal invariant. Okay. So this trick of embedding a non-Markovian process into a Markovian process with a more complicated state space with a murkier ontology generalizes to arbitrarily many degrees of freedom, non-Markovian dynamics of arbitrarily high order beyond second order, stochastic dynamical laws. I was considering the deterministic case, but more famously this is done in the case of stochastic systems where it's well known. This embedded Markovian formulation, however, may have murky ontology, exotic mathematical structures, emergent transformations, symmetries that make its physical interpretation opaque. And indeed, if we're handed such an embedded Markovian formulation at the outset, we might be debating what its interpretation is all this time. All right, so I'm going to now talk about very interesting reformulation of quantum mechanics. So what is a closed quantum system really? A closed quantum system with some state vector psi of t evolving according to the Schrödinger equation. Here I'm using units where h bar is 1. Is a Markovian process, first-order dynamical equation with a famously murky ontology, a set of very weird unitary symmetry transformations. It involves the complex numbers. That sounds very familiar. One might now naturally ask, is there some non-Markovian system with a more transparent ontology for which this Hilbert-space formulation is merely its Markovian embedding? And remarkably, the answer turns out to be yes. As a hint that this might be true, it would be conceptually helpful to replace the Hilbert-space formalism with an alternative. Okay, so there's a little-known reformulation of quantum theory as a classical Hamiltonian system of coupled harmonic oscillators. This formulation comes from two beautiful papers. I recommend reading them. They're beautiful papers. Franco Strocchi's paper, Complex Coordinates in Quantum Mechanics, Reviews of Modern Physics, 1966. And Strocchi-Heslot's paper, Quantum Mechanics as a Classical Theory, Physical Review D, 1985. A couple of people independently discovered these as well. But this is when physics journals publish really beautiful, creative papers. Yeah. So for the generalization to infinite dimensional Hilbert spaces, by the way, because I'm doing the finite dimensional case here, you can see a 1999 paper by Ashtekar and Schilling, Geometrical Formulation of Quantum Mechanics, in a book. So you're welcome. This is generalizable to the infinite dimensional case, but we're going to stick to the finite dimensional case for now. So consider a quantum system with an n-dimensional Hilbert space H, state vector psi of t, and Hamiltonian H equals H dagger. Schrödinger equation is as follows. But I'm using a color coding scheme where law-like things are brown, just for fun. Pick an arbitrary orthonormal basis, decompose psi of t and h into their real and imaginary parts. So we decompose psi into its real and imaginary parts. The 1/2 is just a useful normalization. We decompose the Hamiltonian into its real and imaginary parts. The self-adjointness of the Hamiltonian implies the following conditions on the coefficients. And then the Schrödinger equation becomes as follows. We then substitute in all of these expressions in terms of these real-valued quantities. The Schrödinger equation becomes the following equation. And then these ultimately reduce to a system of 2n classical Hamiltonian equations of motion. They have exactly the same form as the classical Hamiltonian equations of motion for a classical Hamiltonian HCl, which is given by the following classical formula. Notice that this is a quadratic Hamiltonian, so this describes a system of coupled harmonic oscillators. Schrödinger time evolution is therefore isomorphic to the dynamics of a system of classical coupled harmonic oscillators. And in fact, if we'd picked the energy eigenbasis, that corresponds to picking the normal modes, we would have had a system of n uncoupled harmonic oscillators, equivalent to the Schrödinger equation. Mathematically speaking, this is arguably the simplest description of the evolution of any quantum system. What could be simpler than uncoupled harmonic oscillators? And by the way, changing orthonormal bases on the Hilbert space literally is carrying out a certain kind of canonical transformation, those transformations that mix up the x and y I was talking about in this picture. So we see a clear linkage between these two symmetries. Okay, so one chooses, this is now just an aside on Everettian quantum theory, if one chooses to reify the Markovian picture of quantum theory as a first-order dynamical equation, it's not immediately clear why the Hilbert-space formalism should be favored over, say, the Strocchi-Heslot formalism. But then what is to keep us from saying the universe is therefore just some collection of uncoupled harmonic oscillators? And if you think of the universe as a set of uncoupled harmonic oscillators, then certain questions that seem obvious in the Hilbert space picture become much less obvious. Like, for example, why would having zero amplitude, for example, for a branch or a world mean that it doesn't exist? When a harmonic oscillator has no amplitude, the oscillator still exists, right? Whether it's oscillating or not doesn't mean anything. And so things that seem obvious or trivial or just come out of the mathematics really don't. After all, harmonic oscillator isn't oscillating, still exists. And this is the danger of trying to build an ontology directly out of a purely mathematical structure. Mathematical structures are very malleable. They have many different looking formulations. And if you're trying to build out of a mathematical structure, what fixes the mathematical formulation to be one over another? For a quantum system with an n-dimensional Hilbert space, the Strocchi-Heslot formalism has a continuously infinite state space of dimension 2n. And this means that even for the simplest possible quantum system, a qubit, the Strocchi-Heslot state space is continuously infinite. Okay? So, and by the way, this is to be contrasted with the second order case, right? We had a second order deterministic system. We only had to double the configuration space. Here, we have to go from a qubit, which is the simplest possible quantum system, to a continuously infinite configuration space. So what this is suggesting is that if there exists some underlying process with a relatively simple configuration space and a transparent ontology, it's a strong hint that whatever its dynamics is going to be extremely non-Markovian, far more so than second order. And this brings us to indivisible stochastic processes. So an indivisible stochastic process is a simple generalization of a non-Markovian stochastic process. I claim it is exactly the kind of extremely non-Markovian process we're looking for, that the Hilbert space formulation of quantum mechanics is its Markovian embedding. The fixed ingredients, which are the same in every run of the system, are kinematically a configuration space, just like for a classical system. And the dynamics is now not going to take the form of differential equations because it's not a Markovian system. It'll take the form of a collection of first-order conditional probability maps. These maps gamma should be understood as describing the conditional probability to go from a configuration at t0 to a configuration at time t. Okay? So they're maps from two copies of the configuration space to the closed interval from 0 to 1. The events t0 where you can condition on are called division events. I'm not going to have a lot of time to talk about division events in this talk, but I talked about them in many other talks, which you can find online and also in the papers. The contingent ingredients, the ingredients that can differ from run to run, are, well, for times t, whatever the instantaneous probability distribution of the system is, and this could be different depending on every time you run the system. These are the axioms. These replace the axioms of quantum mechanics. By the way, there's a linear marginalization rule now that connects the probability distribution at time t0 with probability at time t, and that's going to be important. Okay? It's going to be important for later. All right, so indivisibility is a simple and remarkably new idea. You can think of it as a failure of iterativeness. It originated in the theory of quantum channels very recently in a paper by Wolf and Chirac in 2008. But it was first applied to classical dynamical systems in 2021. That is the first time it appeared in literature. So this is like brand new. Apparently people didn't think about this before, in a review article by Mills and Modi. And even then it was a throwaway comment in a figure that didn't play a role in their paper. But basically what indivisibility just says is, if I want to evolve my system from t0 to some time t, or from t0 to time t prime, those are in my laws. But there isn't necessarily in my laws, in the nomology, a way to evolve from t prime to t, right? The laws are too sparse to in general allow this, right? So no such purple matrix there exists. Unlike for a textbook non-Markovian stochastic process, usually we think of non-Markovian processes in the textbooks. We specify all these higher order conditional probabilities. We don't specify them here. There's much less structure. Right? But in general, this is going to be a non-Markovian system of infinite order, roughly speaking. Okay, but now there's a construction. I'm going to argue that we can take this system and write it in a Markovian way, and that's going to give us quantum mechanics. So given an indivisible stochastic process with n configurations, I'm doing the finite dimensional case here just for simplicity, we introduce a not unique, complex n by n matrix theta, according to the following rule. So theta is not uniquely defined. What I'm doing is taking theta to be a complex matrix n by n with the property that when you mod square, norm square its entries, you get back the entries of our non-negative matrix, a matrix non-negative values gamma. Okay? This is the collection of the conditional probabilities. Theta is not unique, and this leads to a very interesting new form of gauge invariance that I cannot talk about. This new matrix satisfies the following sum rule. If you square its entries and sum down a column, you get 1, and this is just coming from the fact that probabilities sum to 1. I have to emphasize here that we square individual entries here. This is not a matrix times a matrix. We square the individual entries. Okay, so if gamma happens to be what's called a unistochastic matrix, a term that was introduced by, the idea goes back to Alfred Horn, a mathematician in 1954. But if it happens to this property, it's a unistochastic matrix, then by definition what it means to be a unistochastic matrix is that there exists a theta that is unitary, and so you can assume theta is unitary. If not, and here's a new result, if gamma is not unistochastic, if it is not simply a matrix whose entries are the mod squares of the entries of unitary, we can still pretend that it is. You can take gamma, there's this construction where you can write it as what's called Krauss decomposition, the details don't matter so much, and do what's called a Stein-spring dilation using a theorem due to Stein-spring in the 50s, and obtain a unitary matrix on a slightly bigger Hilbert-space. Okay? And this means that our system, our indivisible stochastic system, has a representation as an emergent quantum system in the Hilbert-space representation with unitary evolution, and you can show that that linear marginalization rule we said way at the beginning becomes linear time evolution, so now we have an explanation for why time evolution is linear. Now, what's crucial about this construction is that for n bigger than 2, for quantum systems more complicated than, bigger than two-dimensional Hilbert spaces, an n by n unistochastic matrix will not generally have a real representation. If you want to take advantage of the fact that we can represent the dynamics using a unitary operator, you might go, well, can I take it to be a real orthogonal matrix? And the answer is, for n bigger than 2, in general, the answer is no. Okay? Therefore, to exploit this stochastic quantum theorem connecting the stochastic process and quantum theory, and to be able to use unitary evolution, you will need the complex numbers or an algebraic construct equivalent to them. And that's fine, because from this point of view, the Hilbert space picture is just a fiction. Right? It's just a Markovian embedding, and so we might as well introduce the complex numbers for fun and profit, because we can do all these other cool things with them if we introduce them. Actually, and this brings us back to the pseudo-quaternions, because we have time reversal in quantum mechanics, we'll also need the k operator, so there's a sense in which quantum mechanics is not really based just on the complex numbers, but also on the pseudo-quaternions, although we don't use k in the construction of observables in quantum mechanics. Nonetheless, it's in the Hilbert space. If the density matrix happens to be rank 1, then there exists an n by 1 state vector psi that gives the following simple factorization. This is now all very familiar. The state vector that you can show satisfies the Schrodinger equation. This linearity of the Schrodinger equation descends again from that linear marginalization rule. So wave functions of the Schrodinger equation are secondary pieces of derived mathematics. They're not primary ontological furniture. This Schrodinger equation is like the Markovian embedding equations we talked about before. So we see from this picture that wave functions are not purely epistemic. They encode a blend of epistemic and also nomological information and are not physical or ontological objects. They are like Magritte's pipe on that first slide. They're like the ether. We thought that they were real and physical things, and it turns out that they're not. The standard unitary Hilbert space formalism yields a divisible first-order differential equation for the dynamics, as we can see here. We can also go the other direction. If you're given a quantum system, you just pick a convenient orthogonal basis, which corresponds in the Markovian embedding story to picking some convenient choice of variables, some canonical transformation or canonical frame in the Hamiltonian, classical Hamiltonian formulation. You pick that, You square the entries of the time evolution operator, you get this matrix. This matrix is unistochastic. By the way, we also pick an orthogonal basis just to define path integrals in quantum mechanics. This is well known. You might think we're losing phase information when we do this. How can taking the mod squares of the time evolution operator and losing all that phase information, I mentioned that was going to be important later on, how does that give us an empirically adequate description? And the answer is, remember, all empirical results come from measurement processes. These should now be modeled explicitly using measuring devices treated as other stochastic systems. And you can just show, and I don't have time to show this, that if you take a measuring device and you stick it in your system, you regard it as a subsystem of the overall indivisible stochastic process, you write down a very simple stochastic process for the entire thing, then you'll see the measuring device will evolve to one of its final readout configurations with the correct Born rule probability, and the phases don't matter. If we want to remove the measuring device and treat it as a mental construct, then we need to keep track of the phases. The phases are a way of keeping track of the missing measuring device, and then we go back to the usual textbook postulates of quantum mechanics. So we arrive at a stochastic quantum correspondence, according to which the Hilbert-space formalism serves as a form of analytical mechanics for stochastic systems, giving rise to an effective first-order differential equation. This correspondence is many to one in both directions. This is a nod to Eric Curiel. This is like how classical mechanics based on second-order differential equations have a many-to-one correspondence with first-order Hamiltonian phase-based formalisms. Like any form of analytical mechanics, the Hilbert-space formalism provides a powerful set of mathematical tools for specifying microphysical laws in a systematic manner, for studying dynamical symmetries, and for calculating predictions. So let me conclude. So what we see at the end of this is one can regard a Hilbert-space quantum system as a Markovian embedding for an indivisible stochastic process with a classic-like ontology without any complex numbers. This next statement will be controversial. I argue elsewhere that this is in fact a causally local hidden variables theory based on simpler axioms than textbook quantum theory, arguably without a measurement problem and deflating a lot of the exotic talk about quantum phenomena. If there are no physical wave functions, there's nothing to branch, and there's no many worlds. The causally local part is related to a new way to think about about causation, which I cannot talk about in this talk or even in the Q&A, but is in other talks and in my papers. But roughly speaking, you have to ask what it means for something to be causal. Bell uses a particular definition of causal. There's a certain definition of causal influences that's pretty typical in literature. But basically, if you challenge that definition of causation and replace it with one that's a little more robust, then there's an argument that quantum theory can be phrased in a causally local way. There are many prospects, future research directions here, applications of dynamical systems and stochastic processes, new algorithms for quantum simulations, new ways to think about quantum causal models, implications for old problems in statistical mechanics. Wayne gave a talk, Wayne Merville gave a talk about about probability showing up in statistical mechanics, and obviously there are questions about can that happen in a theory that's ultimately got deterministic dynamics. Well, if you're saying the dynamics of nature is ultimately indeterministic, then that has some interesting ways to think about statistical mechanics. Ramifications for algebra first approaches, I'm thinking a lot about those, generalizations of quantum theory because we're not starting from Hilbert spaces, and perhaps new possibilities for quantum gravity. All right, that's it. Thank you.